Buenos días a todos, muchas gracias por estar presentes en la última sesión del seminario del semestre 2025-1. El día de hoy tenemos el placer de tener al doctor Henrik Eklund. Él viene de la Agencia Espacial Europea, formado en física en la Universidad de Oslo y posteriormente postdoc en la Universidad de Oslo, postdoc en la Universidad de Estocolmo y actualmente investigador en la Agencia Espacial Europea. Entonces, we're very pleased to have you here. Thank you very much. Pues los dejo con él y que disfruten la plática.
So thank you for the introduction. I will be taking the presentation in English, but if you want later to also ask something in Spanish, it's perfectly fine for me if we do it slowly, or maybe with some translation. So it's with great happiness that I'm here today. Sorry, I realized I wanted time myself. I was myself as an exchange student here, now maybe 7 years ago or something like that, but in Cuernavaca and not here in the city, but in Unam. So it's a pleasure to be here again. And I will just talk about a little bit in general the what let's say we do to observe the sun to facilitate safe space exploration. And I will start a little bit general and then wean more on my interests. So the European Space Agency has a lot of different satellites, and here is an example of this that are the cosmic observers, the ones that look at other stuff outside of the solar system. And this is just to show. Here we have the solar system explorers, the satellites that are around now in or the missions that are thought of in the solar system. And then I also have a lot of Earth observation missions that for various reasons looks at Earth. Some of them science. I'm not really familiar with this. Why I'm showing this is because there are a lot of missions and huge amount of money invested in satellites. And one of the important things is to keep these satellites safe. And that is why one of the reasons that we observe the sun. So we then have a few of those satellites on the second slide do observe the sun. And why we do this is then to predict and forecast for space weather and violent events. And this is then to protect instrumentation, the satellites, and then also to facilitate safe space exploration for future missions, for astronauts. And and so how we do this is then through observations. We have the satellites, we have ground-based observatories here at Earth, and there was also, let's say, intermediate with high-altitude balloons, where they put instruments and they measure for a relatively short period of time. And we also do this with simulation models. So we have simulation models that take up different type of physical regimes, depending on what we want to look at in the sun. An important thing here, if no one is familiar with this, or for people that are not familiar with it, the sun is, there is a lot of things going on there. It's heavily dynamic. And so, we observe the sun in many different wavelengths with many different instruments because they probe different physical parameters and physical layers also in the sun and different temperature regimes. That's the most important thing. So the temperature of the solar atmosphere is very peculiar, and this is something that is still not well understood. How the energy is transferred from, we have here a plot of the temperature as a function of the height above the photosphere, and here at zero, this is the photosphere, what you see if you see a visible image of the sun, let's say. And so the temperature decreases a little bit by distance. But then suddenly it starts to increase, and then in the chromosphere, and then at certain what is referred to as the transition region, it increases super much to a million degrees of Kelvin. So in the corona, it's very hot, and then this process is not that well understood. But on the same time, the density of the atmosphere of the sun, it decreases on average by height. And so there is significant different, let's say, plasma regimes in these different heights, in the different regions, and that's why we need different approaches when we model them. And so this could represent an average model of the whole sun, but we also have a lot of small-scale structures, and here is just an example of sunspots. And why we want to look at this then, so it's a lot of things here that are not well understood. And for instance, the heating of the corona. And what I will go in on a little bit later, with solar flare formation, it is, and potentially coronal mass ejections. It's when a lot of material is bursted out from the sun into the solar wind. And then the sunspot formation, it's also not, there are things that are not so well understood. And I put in a picture here just to show that the magnetic field polarity of the sun, it's more or less every 22 years it comes back to the initial configuration. So at every 11 years it changes the polarity, and this is also not very well understood. And this also comes with the solar cycle. The sun has a 11-year cycle, which you have much more presence of activity like sunspots and active regions. And then it decays. So right now we are in a maximum. So that's also why maybe you see in media there is a lot of posts about solar flares and radio blackouts and these things here on Earth. So one of the flagships that ESA has, it's the Solar Orbiter. It's a satellite consisting of 10 instruments, and it has both remote instruments and in situ measurements. In the remote, and you see we take images of the sun in visible light, ultraviolet, and X-ray, and in situ measurements, that's it doesn't show here. Yeah, it shows by the color. But a few instruments that measure the solar wind plasma and waves and electromagnetic fields and energetic particles that comes from the sun. And it's launched a few years ago, and the nominal mission is ending 2 years from now, more or less. But it already have an extension, so I think it will go on for additional some additional years. And here is an example of the Solar Orbiter, how the orbit of the Solar Orbiter. And the interesting point here, so I put the plot over here. So this is the position it has today. And this is quite a nice web page where you can go and you can explore yourself, and you can drag the time and you can see how it moves and where it will be. And also, so now it's right in between Earth and the Sun. But right here before, maybe a month ago, then we were somewhere here, and we had a really interesting observational program that I was involved in. So the interesting point here is that as the time passes, then they would use Venus as a gravitational booster for the orbit of Solar Orbiter. And so for each passage, it will gain a little bit more inclination, and this is something that is really novel with the Solar Orbiter. That with the higher inclination, it will go up towards more than 30 degrees, more than 33 degrees, and with that we can see the solar poles. And that is for many scientific reasons, very interesting to see, because the solar poles differ very much from the solar equator. And I put in this here. So these are just plots showing the distance to the sun and the latitude over the equatorial plane. So here we are today. We just came out from perihelion from this in the orbit. We were really close to the sun at 0.29 AU, astronomical unit. But here in 2027 we will reach the closest and at 0.28, a small difference, but it's still, the further close you are to the sun, the more high resolution you get. So it's quite important. And here this plot then shows the inclination. So in the next perihelion that comes in March of 2025, then we will have, I think it's more or less 17 degrees. That's very, that will be very interesting. So here we start with a little bit what I'm looking at with this data, and this is an example of the extreme ultraviolet observations of the sun. Here is a zoom in the white square, and here is an additional zoom in the red square in this one. And the interesting part here is that you see in some locations very small brightenings, and these brightenings catch interest from many people when we got these observations, because as we are so close to the sun now with this instrument compared to other instruments that we have, then we can see these brightenings at even smaller scales than we have seen before. And that also challenges a little bit the formation process of them. And the thing is that we see so many of these events that if one just make an estimation on the heating that would, or energy that would come from one of these events, it's so many that it could maybe have a significant contribution to the heating of the corona. As you remember, in the first part of the corona was very hot. People might have different opinion about it, but that's not the only interesting reason for why I want to look at it. But the important thing here is the energy budget between the chromosphere and the corona. They obviously have influence on it. So the really high intense events estimated about 1 megakelvin, and there's so many, but they also have a surprisingly low formation height. So in temperature they are where we would place them in the corona, but in many of them seem to be lower down than we would expect. So there is one popular model. I don't list different type of models here, but the most popular, if you would ask someone about it, they would say, yeah, it's because of magnetic reconnection. And this is then, so with this model, it interests me very much, because then there are so many that we can study these events statistically. And if they are represented by magnetic reconnection events, then it also allows us to potentially understand more on how they form and understand how larger reconnection events form. And larger reconnection events are known as solar flares. And here we have an example of this, how a reconnection event works. You have these magnetic field loops, and you have these of different polarities. And so, and when you have dynamics and movements going around in the atmosphere, you can get these magnetic field lines very close to each other, and at some point they can reconnect. And if that happens, there are different scenarios there also, but one of these scenarios is that you can get these a lot of let's say energy release upwards here and also downwards, and that can also release a lot of materia into the interplanetary space. And so yeah, so the model is that these ones could be small, very, very small versions of this. So then, to study, we can then study the connection between these ones and the larger scale solar flares. And that is so a large scale solar flare, it's basically just a sudden increase in electromagnetic radiation. and it can be really intense, and it can also be very weak. So you have this classification from A to A, B, C, M, and X. And X class is really, really strong. We don't get many of those, but we get many of these smaller ones. And so as I said in the earlier plot, these ones can give rise to particle acceleration or coronal mass ejection when you get a lot of outburst of material. And this then is really potentially, it could give serious damage to instrumentations and satellites. But it can also be, as you see here in this plot, we can get these radio blackouts at Earth. And that is because the radiation ionizes part of our atmosphere and creates a lot of trouble. And that can also give this kind of trouble, that the atmosphere can suddenly expand, and that can also create higher drag on low orbit satellites, and that's really an issue nowadays with a lot of satellite development. And in general, this is very important to study because of facilitating the safe space exploration. But these particles, if we get charged particles towards the Earth, it can also give rise to something more fun or more beautiful, at least, with the aurora borealis. And it is practically then the solar wind. The charged particles comes in here and hits in generally the poles of the Earth. And I just wanted to put it here, so this connection to the more beautiful stuff and not just the troublesome stuff. So if these solar flares give rise to charged particles, to accelerated particles, then we can also see them with in situ instruments. The solar orbiter in the earlier plots I showed has a few of these instruments. And this is a plot showing for a specific date an example of, so you have the sun here in the center and you have the different satellites at these positions. So these are different satellites that we use to study the sun. And I put this example here because this arrow here would, for instance, model a solar flare, a potential outburst of particles, and then they would, if they would travel with a certain normal speed, then they would encounter here the solar orbiter. So this is an event that we're looking at. So with these instruments, it allows us to link the particles that you see in the satellite to a specific event at the sun. So this was the let's say a little bit sidetrack with the solar flare kind of model with the small scale dynamic features that we saw. So that's one of the reasons that we want to study them. But as a means to study these small scale features that we see, then they are in the lower corona. But then we are interested to look at the chromosphere, the underlying layer of the solar atmosphere, to see how the dynamics there happen to give rise to these small scale events. And that is something that we can do with Atacama Large Millimeter and Submillimeter Array. I didn't put much introduction to this here, but this is an antenna array that is in Chile, in South America. And it consists of more or less 66 antennas, I think, as you see here. More or less 50 12-meter antennas and 12 7-meter antennas. And you who are quick at math, that's an addition of 4 12-meter antennas, but they're used in different ways. That's why I presented like that. So they operate between 0.85 and 3 millimeter, more or less, to look at the sun. And this is very interesting because the radiation here that we measure, this radio radiation, it forms in the chromosphere. And It also has the property here, this is a black body curve, and it has the property that these wavelengths end up somewhere here, and so you have a linear relation between the intensity and the temperature of the plasma that you're measuring. So you can get a good estimate of the temperature in the layer that you're measuring of the solar atmosphere. So this is from my point of view extremely powerful to observe this. And yeah, and ALMA in its sense, we have had radiant interferometers before, but ALMA is very game changing in terms of sensitivity and angular resolution. And yeah. So an interferometer, I just wanted to go in on that really quickly. It works essentially, so you have all these antennas, and you then calculate the phase differences between the antennas. And so if you have two antennas, then you get, let's say, an image that looks like this. If you look at the point source, it will look like this, let's say a star, very far away. And if you add more antennas, then this is 3 antennas, then you get something like this. If you add more, then you get successively better. And here in the last one, we also have the temporal domain. So we wait and we integrate and let the Earth rotate. Then you get much better. And here you have so this is how you end up with all antennas from the ALMA array. You end up with this type of point spread function. And the only difference here is we cannot use this because, as I said before, the sun is heavily dynamic, so we want to have observations on the order of seconds or 1 second. So there is no new, we cannot rely on the rotation of Earth. So that's also why it's more or less first now, I would say, when we have these many antennas that ALMA offers, that we can have a good observation, a good PSF. So this is an example on how the data that we measure ends up looking. And this is just a very small region of the sun. It's more or less, this is 60 arc seconds diameter, and the sun is 2000 arc seconds diameter seen from Earth. So what I did it is to look at in this data, then I identify all these small scale brightenings. And here is an example plot of that. You see temporal and a spatial plot of that. And a small scale brightening is put this here to show it's just too simple that if you look at a certain location, you see an increase in temperature and then a decrease in temperature. And specifically in this data, then many of them are dominated by shock waves. So the shock waves that propagates from down in the atmosphere upwards. And why they do that is because, as we saw in the previous plots, with the density going down in the atmosphere as you go upwards, then you will the acoustic waves will steepen into shock waves. And this could also then we wanted to look at the correlation to this, if these events can give rise to production of linear particles and production of the solar wind. And to understand that more, because many of these could be something else than that are potentially not shock waves. So to understand that more, then we make use of magnetic hydrodynamic simulations. And I just put it here because it's an example. This is a cross section of a simulation box, and here is the top view of the simulation box. So this then simulates the solar atmosphere from further down than the photosphere and towards several megameters up in the corona. And yeah, so this is a specific simulation that we use. We use this specific simulation because this is it has been optimized for these specific wavelengths. And so by in these simulations, then we have everything at hand. So we can look at all the plasma parameters. So if we see an event, I didn't plot it, but if we see an event somewhere, then we can go in and we can in the simulation look, well, okay, how did the plasma parameters look in the different layers that give rise to this event? And so this is very much useful. I will return to this in a few, but first I will just go in here and show them to run off with observations of these small-scale brightenings. So this is a happy face sun. This was an observation from 2022. So we specifically observed the region here in the nose of this happy face, and this is from another satellite. This is a NASA-led satellite that shows this image, but it's in the same wavelength as you see over here, very similar wavelength. And this is from the solar orbiter. So this is extreme zooming. It's just maybe a few pixels of this image. And so here is an example of one of these brightening events. And you see here's the temporal evolution of it. You see that it comes and it goes, and there is nothing else visible around it. And the interesting part then is why it happens. So then I combine them with everything that I tried to somehow smoothly or briefly present. So I combine these things here. So here we have again this image. Here we have the magnetic field measurements at the photosphere, and this is very useful because then we can see what polarity that the magnetic field has at the photosphere. Then you have these magnetic field loops that connect somewhere else, and often if you have these footprints of the opposite magnetic field polarities very close to each other, they can often cancel each other. But so with this combined, then we can make a good estimation of the magnetic field topology here. And what you see here then, as the line here in the dark red line, this is the observations from the, and the interesting part here was then to see how the chromospheric temperature evolution varies when you see at the same time you see one of these lower coronal events precisely above it. And just an indication that we have here is that there is some sort of chromospheric cooling, and which points towards an energy exchange between the chromosphere and the corona. So this is a paper in preparation. Soon you can read it. So yeah, okay. So some other things that we also can use with the simulations that I just showed you, it is to develop better and refined ways to use the observational data. And this is this is the spectral receiver bands of the ALMA array. Just 3 of them here. We can observe with more of them, but as an example here, so here we have the frequency on the x-axis, and you see these small dots here, and these are the actual receiver bands. So what most people do, it is that you take all the intensities, so you have a lot of spectral channels in these receiver bands, and you take all the intensities and you make one image. But this was a project to develop that we take an image just in each of the receiver bands, in the sub-receiver bands. And that is very useful because so here, but this is from simulation, but then you get these 2 images, they look almost identical, and they more or less are, but there are small differences that actually gives rise to kind of large temperature variations. So see, some areas are blue and some are red, and that means that sometimes one of the channels are colder than the other one, and that means that the continuum intensity, it's either positive or negative. This is just to show that the formation height of the intensities are still always in order of wavelength. So for higher variation forms further up. And why that is important detail, it is because then if you take the difference of the intensities at these different channels, then you get this what is in the middle plot. So here is temperatures of each of the channels, and here is the difference of these temperatures. The blue and the red here we can, it's just that it's two different receiver bands. So it's at 3 millimeter and 1.25 millimeter. But the interesting part here, so as we have different in temperatures, but the formation height is not different, then it means that, well, it's an indication, let's say, of that if you have negative difference or you have a positive difference, it means that you're probing either decline at those at the height that you're sampling. And why is this important? Yeah, then it's important because if you're measuring, for instance, one of these small-scale brightenings, and you see either you have a declining temperature at that point or you have an increasing temperature, it tells very much about the structure of the underlying chromosphere. And I also put in here because it also gives, in this case, what we see here. This is a temporal evolution of just one point in the simulation. And what we see here, it's acoustic waves that are excited and steepening into shock waves. So these ones that you see go up here and here, those are shock waves that's steepening up, and they heat up the atmosphere, the chromosphere here. And then you also have these regions here in between where you have downfalling gas, and sometimes the gas is hot and sometimes it's cold, and so this is where it contributes a lot to our analysis of these events. Yeah, okay, so I've more or less already said this. I just show here is an example of observational data, so this is not from simulation, but the observational data show us the same, or what we expect from the simulations. So here are the intensities and the temperature, as these intensities can be transferred to temperatures. So here you have it between 6,500 and 9,500. And here is the difference between these. So the blue parts here indicate a decreasing temperature with height, and the red parts an increasing temperature with height. Yeah, okay. So now I thought I will go in on another. What is it? Okay, I will take this more rapidly. So this is the again the simulation, and so a problem that I had early on when I was looking at these small-scale brightenings, it was that they appear very much in observations. They appear very dim, let's say, compared to in this what I saw in the simulations, and that is because the angular resolution, even if we have high angular resolution with this instrument, with our instrument, then the features are so small that you get the degradation of this. So if you see this peak here, for instance, with the observational resolution, we get this very small peak here, and that was kind of a problem because you get a degradation of all of these events. So first I started with this just liner, let's say, manual way to try to compensate for the degradation of these type of events. But it goes well, but it gives rise to a lot of error in the correction functions. So instead then I started to analyze this with a deep neural network. And the specific neural network that we developed here is a combination between a convolutional neural network. Those are good to distinguish features in two-dimensional data in images, and a recurrent neural network that is good for handling time series of images. So this is an integrated architecture with both these aspects, and so it's a 2D convolutional long short-term memory neural network, if someone is familiar with it. So what we did is that we take these simulations and essentially then just degrade them to the resolution that where the observations would have, and And then we have a completely separate validation simulation that the neural network never seen. So when we take these ones, we feed the observational resolution data to the neural network, and then we ask the neural network to observe this, to estimate this difference map, that is the difference between this one and this one. And here were the results. So this is the absolute truth. This is the estimation of the neural network. There are a lot of very small pixel-sized features here that are not represented here, but that's very expected because you have a limit of information do disappear when you degrade the resolution. So this it's very good fit we got. This is just another aspect of the results. Some other question we can do now. So here is then the final results of this. Here is the, on the left hand side here is the absolute truth. Here is the degraded resolution, that is how we would observe it with antennas. And here is the output from the neural network. So what I want to point towards here is you see these small scale bright features here. Those are almost not visible at all here in the observational resolution, or they are visible but they can be confused with other features that are not really bright in reality. So if we apply the neural network estimations to the observational data, then we will get something that looks similar to this, where it will bring out the contrast of these features. So in that way, the intensities are recovered. Here is just a zoom-in example of one of these bright features. It's visible, but barely visible, and the analysis will not detect it as one of these really bright features, but the neural network recovers it very well. So yeah, this is just a distribution of many of these small-scale brightening events, and in the observational resolution, and this is in the neural network estimation. So yeah, that's good. So how the neural network handles the data, it is if you have between two parameters. So you have one parameter and you ask it to observe, estimate the other parameter. The more degeneracy that you have, the more difficult it will be. So for instance over here, if you have something that is of 800 here, for instance, this is brightness temperature specifically, then there is very little information to know if it actually corresponds to something that is 500 or 6,000. But over here, it's easier. So essentially this is with the different resolutions that this interferometric array allows us to measure. And yeah, what I realized then is that it can, with this technique, we can measure a lot of different parameters, because the neural network doesn't care if it's temperatures, densities, or velocities, or particle densities. It will not, if we just see it as data. So as long as you have low degeneracy between, and it can be a chain of parameters, significantly low degeneracy between these chain of parameters, then it can achieve well to estimate the parameter that you ask it to estimate. And why this is really good, because if you can, this is just an example, if you have some data point, and then it can be very challenging to manually go through all the steps or manually correlate all type of features, but the neural network, it can do it automatically in a very good way. This is an example of something else then that I realized, the neural network don't only work as the convolver of the data as the previous example. I can also estimate, for instance, the formation height of the radiation. And the formation height of the radiation is very important. Coming back to, for instance, is with the small-scale brightening features, if we get an estimation that the formation height is very high or is very low, it also tells a lot of how the temperature stratification of the atmosphere is. And just to put this briefly, so this is just examples of this is the truth, and this is how the neural network achieves in the right column, and this is the truth. And essentially, the good thing here is that I only input the observation maps, and I get the formation heights out. Here is another example of something that we did in this summer. I had a student with me that was working on this to distinguish at what locations that we have, this is at what locations that we have concentrated formation of the radiation that we see, or when the radiation that we see is formed at distinctly different heights. And why this is important is because in the occasions where you have at two distinct different heights, the radiation function, the assumptions that we do when we use this data, it kind of semi-breaks down. Because then it's no longer one black body radiation from one layer. You might have two distinct temperatures, and you get a sum of those two. So then essentially the temperature that we estimate could end up not even be present in the specific location where we're looking. So then we work on this to, with the neural network, estimate. This is just to show, like in this case, the red areas here would be good estimates of the, with low error on the temperatures that we get out. And so a little bit low on time, so maybe I don't need to go into details here, but this is just also to show in the different ways. So we estimate the formation height at the low height, and then at a higher height. So this is the low height. Here we have low degeneracy of the data. Here at a higher height we have a high degeneracy of the data. So it's more difficult for the neural network to pinpoint, is it really, what height are we talking about here? So this is still something that we are trying to work out to have robust and reliable results. Yeah, so this is what I started with the, as long as you have a low degeneracy, and then you couple any type of parameter to another type of parameter, it doesn't really need also to make sense in the physical sense. So this is just other things that we have tried to observe, to estimate in the solar atmosphere specifically. Something that is of interest of the projects, we are interested in applying this to observe or estimate occurrences of solar flares. We'll come back to another slide of that. And this I found very interesting. So I put this here because I thought maybe it would be of interest for people that do not look at the sun. So this I realized that before then, so I have images that have images of something, of the solar atmosphere, that has done a correlation. So if something happens here and then something evolves, a wave or something, then you will see a connection to that over here in the spatial domain. But here, as long as you have just time series of data, then you can stack them to an artificial image, let's say. And with this, it's very powerful because then you can take the information in the temporal domain whilst you try to find connections between these parameters that you're looking at in this artificial spatial domain. So you can find the correlations in a good way, even if they to each other. And yeah, so I just put it here. If you have any time series of information, maybe this would be interesting for you, depending on what you want to estimate from the data. So I'm starting to get to the end of my I feel very brief, non-in-depth talk of quite many things. So I just wanted to put this out here also, that if there would be someone that would be interested to look on the detection and the classification of these solar flares and prediction, the aim would be to be able to predict these type of solar flares. then we will start this project. And it would then be implementation and development of multi-spec and correlate to Flare databases. There are databases online where all these layers are registered and the strength and these things. And then apply a machine learning algorithm similar to what I've been presenting before of a spatial temporal neural network architecture. And the aim then would be to be able to predict these solar flares. And this could then potentially be, we could profile it towards, ESA is coming out with a new satellite in 5 years or something like that, that will be situated here at Earth Sun Lagrangian point 5, and it will be to monitor the sun and essentially exactly do this to predict and forecast solar weather. So it would be very interesting then to maybe profile this project towards exactly this type of data. If someone is interested, please get in contact. And we have project number 2 that could be if someone is interested. And this is what I realized from colleagues in the faculty here that is working with on PTV, particle tracking velocimetry. I quickly realized that when tracing these type of particles, it's applicable essentially the same type of neural network architecture that I've been working with to estimate their maybe I didn't put it here, to estimate the precise locations and also the sizes of them, because now with current methods it can be a little bit tricky. So if you have a lot of particles for some by coincidence gathering in the line of sight at one point, and then all of them continue in their ways, you can lose the track of which is which. But I think it would be interesting to explore this with this type of approach. And a very long-term aim, I put it here because this is also my interest in it. I think that this could be kind of a proof of concept for studies of the fluids that are under the ice on icy moons in the solar systems. It would be very interesting to, if something could be developed, to profile it towards this, because this is also needed. Can't go in on the details if someone is interested, but if you imagine that you would have a probe and you would drill down and you would have something actually under the ice of one of the icy moons of Jupiter or Saturn, then how would you get the data up? So you cannot have a lot of data, so you would maybe need to have something that directly looks at things and take out key parameters. And or a similar program like that, please speak to me because I'm very interested to get this going. Or please speak to Dr. Arena here. And I did write conclusions, but it's not really. I will leave them here if you want to read, and then I'm happy for eventual questions, which I'm sure there are lots after this message. For all new people that maybe came in the middle, please, if you want to take it in Spanish, it's completely okay. I understand more or less. I can say, yes, 2 seconds. I can say, so I brought a small souvenirs. So people with the best questions will get the best souvenirs that are magnets. Please.
Yeah, I just have a question because you mentioned at the beginning that you were using, I'm not sure if you were using or not, you are using that for the chromospheric magnetic field model or in which part of
right.
research?
So yes, I'm using the solar orbiter data. So I'm working in several aspects with the solar orbiter. And I use some of the data then to look at this, and that would be specifically, can go back here to show So it would be this this type of data that is in the extreme ultraviolet, and it samples the corona or the lower corona.
And then you're using ALMA to get into those maps, right?
So I correlate then the chromospheric measurements that I get with ALMA with the coronal measurements that I get with this. So they're lying just on top of each other, let's say. And then in the solar flare project, then we're working with also more instruments of the solar orbiter, because then many more things becomes useful, like the X-ray and also the in situ measurements to see if there comes particles to the instrument.
Okay, so for the solar flares, that would be using the in situ data, and this is just the
broadly speaking, yeah.
¿Alguna otra pregunta por ahí?
These writing events are measurable via solar wind information?
See if I understand the question right, is if these brightening events gives rise to solar wind, and if you can read off them. That is one of the questions that we want to answer. It's easily said, no, it will not, because these ones are so small in the scale, and they are mostly often seen where you have magnetic field loops. So if you have some particles from these kind of weak events, most of those particles will probably just follow the structure of the atmosphere, let's say. The interesting part here is the really large scale events. Those obviously gives rise to a lot of solar wind and detection in the solar in the in situ measurements. My interest here is to compare these type of events, because if they origin from similar type of event, then that can tell us something. Here we can have thousands of events, so then we can maybe get better to predict when the large-scale events will happen, because that is also, let's say, a little bit by surprise sometimes. Oh, now it happened. So there are many people that try to predict that. So my angle on it is that I would like to do this. Did that answer your question?
Yeah.
Okay.
Can you calculate the velocity of these shocks with the temperature in plasma?
Yeah. But now I have only. So yeah, essentially, so this is a simulation then, but then you can see here the we can calculate. You can see on the how quickly they rise up. That is correlated to how the increase in temperature, and also if you do this, let's say, trick to look at the different channels that I was talking about before, then you can also see by the slope here of how quickly it changes, and you can get an estimation of how quick the shock waves are propagating in the observational data. That's of course, yeah, because here in this.
Las traducimos, no hay problema.
Not I have a question. So it is about the degradation of images. So which is the procedure that you use in order to degrade them?
I just come all with Gaussian kernel.
Okay.
So specifically then for observation, we can check the exact, let's say the exact resolution, and then with that kernel we can degrade the simulations to mimic the observations.
Have you tested the result of the neural network to reconstruct an image from the satellites or the ALMA? I don't know.
From in the ALMA array, yes. Maybe I don't have in this presentation. But yes, with the ALMA data, that's what I've been doing that, and then I do it here, but with these type of results, similar to this. Then this is why I talk about this, is because this is where I started. So I did my PhD on developing to use the ALMA data for observing the sun. But there are other people that would be interested to do this on other wavelengths or other instruments also. But I haven't applied it.
So at the end, when you apply this technique, you will be able to find the frequency of these small bands. Or estimate
maybe,
at least.
yeah. So at least specifically this technique, then I will get a better estimate of the actual temperature that I have.
Mm-hmm.
So the instrument, it blurs everything out a little bit. So then all the bright events appear much colder, and cold places or cold events, they appear a little bit brighter because of the smearing with neighboring events. So it's just a deconvolver technique to recover a more reliable temperature. And it's very good then, because if I want to be able to see the heat exchange between the different layers in the atmosphere, then this let's say lowers the error bars significantly.
Mm-hmm. ¿Alguna otra pregunta? So if there are no more questions, let's thank Henrik again.
I will put here on the front table, there are some stickers and some magnets. Please feel free to take, but with modesty, it's enough for everyone, please. Sorry.